So question A says that when the box is up there, what is the minimum velocity of the box that will allow it to successfully make it through the looped track? Well, this is a net force equals MAC question. And like any net force question, I'd probably start by asking myself what forces are acting on the box when they're at the top there. So, Bella, what forces are acting on the box when it's up there?
Gravity.
Okay. I think gravity's probably a good call. What else?
Normal force.
All right, I'd go with normal force, yeah. It's in contact with the track. Now, I'm going to make downwards positive because like any problem in which there's an acceleration, I think it's best to make the acceleration the direction of positive, and downwards is that direction. It's got to be traveling in a circle. It must have an unbalanced force towards the center. So I'm going to say that that is mv squared over r on the left, and normal plus mg on the left, and m equals v squared over r on the right. Good so far? No, this part isn't surprise. I mean, the faster this thing goes, the bigger the normal force will have to be. Right, because I have v squared over here. If that gets bigger, something on this side has to get bigger. The only thing that can actually change is normal force. So if I go faster, the track has to push harder on the ball. If I go slower, the track can push less on the ball. If I start going too slow, though, the track's going to push less and less and less until the force from the track goes to zero. That's the slowest I can go is the moment the force of the track goes to zero, because anything after that, I'm no longer touching the track. So that's where my minimum occurs. So cancel out the m's because there's one in every term. And v min equals the root of g over r. All right, Bella? That good so far? B, find an expression for the height the block attains after successfully traversing the loop in part A in terms of r, m, and any fundamental constants. So I believe they're asking me to figure out how high above the baseline the object will be after it makes it through the loop. So that's fine too. This sounds like a conservation of energy problem. It's asking for a height. And like I said, conservation of energy is pretty good at telling us speeds and displacements. In this case, it's the vertical displacement. So I'm going to start by looking at this problem and realizing the box has a velocity this way and is above the reference level. So I think the box has kinetic energy and it has gravitational potential energy. Is that a pretty reasonable assumption? I want to find the maximum height attained by the block. Well, the maximum height attained by the block suggests the block is going to have gravitational potential energy there, because I'm looking for a height. But I also think that the block is probably going to have no kinetic energy at this point. If it's at the maximum height, it shouldn't be moving upwards anymore. And if it's moving downwards, then it's already left the maximum height. So I don't think the box is moving. I think this is where it comes to rest, as high as it's going to get. Is that good for you? All right. So on this side, I'll have 1/2 m v min squared plus, well, mg. Now, h minus h naught. Somebody in 7th period was kind of freaked out. Like, I don't get the h minus h naught. So if that's you and you're just unwilling to ask a question about it, this is just telling you that you need to pick where your reference level is. This whole thing is just how high is the object. But it's asking how high is it from the reference level. So I'm saying you pick where 0 is. I think 0 is here. And I'm going to say that the object, when it's here, oh, yellow's not a good choice. When it's here, is 2 radii high. So I'm going to use for h minus h naught, 2r. Any questions about that? All right. Over here, I'm going to have just m, g, h. I'm looking for h, the height that it attains. All right. I'm not allowed to have v in my answer. So I'm going to substitute this expression I just found for v. So 1/2 m square root of gr squared plus mg times 2r equals mgh. I wish to find h. Square the radical and it goes away, and I'll have 1/2 mgr plus 2 mgr equals mgh. I notice that I have an mg in every term. You guys notice that? So I'm going to cancel out mg in every term, and I'll get 1/2 r plus 2r equals h. 1/2 plus 2 is 5/2, so 5/2 r. Yep.
Can you explain why you can't have velocity in your answer?
Because it said in the problem in terms of r, m, and any fundamental constants. Just doing what I'm told. All right, so we finally make it to your question, C. Since this is only a model of a real roller coaster, a spring launcher is going to be used to launch the block into the looped section. The block is pulled back against the spring launcher and released. The launcher has a spring constant of K and is a linear spring. What displacement of the spring will successfully launch the car through the loop in terms of M, R, K, and any fundamental constants? All righty. I'm going to point something out to all of you that you may not be thinking about, but this right here represents the total energy in the system in terms of M, G, and R. I'm going to encourage you to consider what I'm saying here and maybe write some notes down. We figured out the energy in various places here, but we're only allowed to use M, G, R, and K in our answer. Right here, this is the total energy the object had. It's the kinetic energy and the potential energy when it was at the very top. And when I add those things together, I get 5/2 mgr. That is the total energy of the system. And yes, we set it equal to mgh over here, but that was to find an expression for h, how high it will go along the ramp. But this is the total amount of energy in terms of m, g, and r. And I don't know that you guys kind of put that together, but that is adding together the kinetic energy and the potential energy and putting it in the terms we're allowed to use. You often miss that. And so we know that right here because we added it all together. This is the total energy in the system. So somewhere before all of this, the block was pulled back against a spring. That's what they're telling me. The block was over here, pulled back against the spring. And I don't know how far back it was pulled, some delta x, and the spring has a spring constant K. And then the block was launched from here. Is all good with that? Because this part's the important part. The energy in the spring has to be equal to 5 mgr. Because that's the energy the system has to have for the box to make it through the loop. So I'm going to say exactly that the energy of the spring here has to be equal to the gravitational and kinetic energy that the box has here. Any questions about that? Because I think that's a big deal. And if you don't have questions about that but didn't know to do this, I would encourage you to maybe write yourself some notes. We are doing this because the energy at the spring has to be equal to the energy that it has at the top of the loop. So I'm setting those two things equal. This is the spring. This is the top of the loop. Because only at the top of the loop were we told everything about the energy. And the energy has to stay the same for every part of the problem. Now from there, I can just say 1/2 K delta X squared equals 5/2 mgr. Now I just have to solve this for delta X. So that's algebra. I'll multiply both sides by 2 first to get rid of the fraction. Divide both sides by K to isolate delta X. I'm going to take the square root of both sides. It's a lot of algebra, but it's really not that much algebra. Yep.
For the energy in the spring being equal to the energy at the top of the loop, it's not like that it has to be specifically the top of the loop. It's just where you receive the information about where.
Yeah, because that's what I had.
Okay.
Yeah, they'd give, if I had something else about energy from somewhere else, I could pick any other place, yeah. I just know that the energy has to stay the same, and that was the one place where we had both energies. Does that make sense over there? Yeah. All righty. It is found that while using the displacement of the spring in part C, that the block consistently loses contact between the block and the track as it makes its way around the loop. 2 students argue about the reasons why. Student 1 indicates that the spring is likely not perfectly linear and that it holds less energy than it should at the displacement they calculated, while student 2 believes that there is friction along the track. Although both students may be right, each student proposes a test to determine who is more correct. Student 1 suggests pulling the spring back further and trying again. Student 2 suggests starting the block on the ramp and running the block backwards towards the spring. Which student's test has a better chance of determining who is right? I think that's a pretty hard question. Which student do you think has a better chance? Nobody? A spring of spring constant 7,500 newtons per meter is placed in front of a curved ramp as shown. A 5 kilogram box is pulled back 20 centimeters against the spring. So we've got this track-like looking thing. Like so. And there's a box. Pulled back against the spring. And they tell us that the spring constant is 7,500 newtons per meter, and the box has a mass of 5 kilograms, and that the box was pulled back a distance of 20 centimeters against the spring. Question A. How much work is done on the spring when the box is pulled back 20 centimeters against it? The work done on the spring is equivalent to the elastic potential energy stored in the spring. So I'm going to start there. I don't have to actually calculate work because I can't. The force from a spring is not uniform, so I can't use the work equation here. This isn't kind of one of these things that you're going to have to start getting accustomed to. They asked for work, but what you're really calculating here is how much energy is in the spring. So I'm going to do 1/2 times 7,500 times 0.2 squared. I have to convert that to meters. And I don't know what this is, but I'm sure I can find out. I get 150 joules. Question B. How much elastic potential energy is stored in the spring? 150 joules. That okay with all of you? Not terrible? Question C. Assuming the floor and the ramp is frictionless, how fast is the block going after it leaves the spring? All right, so this sounds like a conservation of energy question to me. It's asking about velocity, and it's talking about the thing being launched from the spring. So I kind of see two states of this problem. The state where it was up against the spring, and the state where it's now been launched and has some velocity. You guys all good with that? I think we have elastic potential energy here and kinetic energy here. And since the height of the object never changed, I'm not going to consider anything in regards to gravitational potential energy. And I'm going to state that the 150 joules of energy that the box had as elastic potential energy is now going to be in the form of kinetic energy. Does that make sense? All right. The box has a mass of 5, and that's it, mass of 5. So 150 equals 1/2 times 5 times v squared. So that's 150 times 2 is 300. 300 divided by 5 is 60, I think. So 7.7 meters per second. Anybody else get that? Seems good to me.
I got it.
Woohoo! I feel good today. Question D. If the ramp is 0.5 meters high, how fast is the block traveling when it makes it to the top of the ramp? Okay. So now the block is right here at the top of the ramp. And it says how fast is it moving, so I think it's a suggestion that it might have some kinetic energy there. But it is now definitely above the reference level, a height of 0.5 meters. So I think we're going to have some gravitational potential energy, and we're going to have some kinetic energy there. That all makes sense to you guys? Now the box still has 150 joules of energy. That hasn't changed. But now we are at a height of 0.5, and we're moving, apparently, at some speed, and we don't know what that is. So we just have to figure out V. So 150 equals 5 times 10 times 0.5 plus 1/2 times 5 times V squared. 5 times 10 is 50, times 0.5 is 25. Subtract it from the other side, I'll get 125 equals 1/2 times 5 times V squared. So that's 250 divided by 5 is 50. So V is the square root of 50. I don't know what that is.
7.1 meters per second.
So it's still zooming. Still zooming. All right. Moving along, if the box leaves the ramp traveling straight up, what is the maximum height achieved by the box? All righty. Well, I think they're suggesting the box is going to go zooming into the air somewhere way up high. Right? Would you guys agree? And the maximum height will be when it only has gravitational potential and has come to rest. Does that make sense? Excellent. So, question E. I think we'll just say there's still 150 joules of energy in the box. And that has to equal mg and whatever this height of the box is. And it looks to me like that's going to be 3 meters. We doing okay so far? I mean, this problem is asking all the basics. Right? We've got spring energy, kinetic energy, combination, and all potential. All the basics have been asked. When this toy is actually created, it is impossible to eliminate all the friction. When the box is launched, it only makes it 2.5 meters at its maximum. How much work was done by friction? Well, at its maximum, it doesn't make it 3 meters into the air. It makes it 2.5 meters into the air. Regardless of what has happened, at this moment, the object actually has 5 times 10 times 2.5 worth of energy, right? I'm just calculating the amount of gravitational potential energy it has right now. And that's 5 times 10 times 2.5. That is 125 joules. We know the spring has 150 joules. So it starts with 150 joules, but it actually makes it to the top and only has 125 joules. That suggests that 25 joules of energy was taken away by friction. But I might even write that as negative. Work done by friction was negative 25 joules as it took that energy out of the system. If a more massive box is used instead, how will this affect the height achieved by the launcher? It will be less. And the issue comes down to the fact that I have the same amount of energy in the spring. The mass of the box doesn't change what the spring has for energy. But this box is going to be harder to push, isn't it? So it won't be traveling as fast, and it won't make it as high. Now, the same amount of energy is in there, but if you'll notice, in every one of these questions, like right here, or say right here, we had to divide by m. If m got bigger, that means the velocity got smaller and the height's going to get smaller. So it's just that that box is harder to push. So less. All right, a 2-kilogram hammer is lifted 1 meter above a nail. How much work is done lifting the hammer? So we're going to have to start blurring the line a little bit between work and energy. So the hammer was lifted 1 meter above the nail. And it's a 2-kilogram hammer. Once up there, it's going to have gravitational potential energy equivalent to mgh minus h naught. So the work done in lifting the hammer becomes energy. So I'm just going to calculate how much energy it has, as that would be the work done lifting the hammer. I could do force times displacement and cosine as well, but we did that and got this formula already. So it's just a little more straightforward for me to say this has got to be how much work was done lifting the hammer. Oops. So it looks like 20 joules of work was done lifting the hammer. Now, it says how much work was done, so it didn't specify whether that work was done by me or done by gravity. If it was the work done by me, it'd be 20. If it was the work done by gravity, it'd be negative 20. because the hammer went upwards, but gravity was pulling downwards the whole time. They weren't specifying, so we're just going to say 20 joules. Either way, this is the amount of energy that's now in the hammer. What is the potential energy of the hammer due to gravity? 20 joules. So this is A, and B is just the same thing, 20 joules. It was the work done on the hammer. And I hope you understand that having A and B there is to drive home the fact that we're talking about the same amount of energy. C, the hammer is released. How fast is the hammer traveling just as it strikes the nail? C sounds like a conservation of energy question. The hammer is going to fall to here just as it contacts the nail, but now it's moving. So I am going to set or assume that in our heads we have set the reference level to be here, and we were 1 meter above here. So now I'm going to assume we are at the reference level, and that means there's no potential energy, but I probably have kinetic energy there. So this 20 joules has now been converted to kinetic energy. The mass of the hammer is 2, so the velocity is the square root of 20, whatever that is, 4 point something. 4.5. All right, the hammer comes to rest against the nail and does not bounce. The nail is pushed into the wood 0.5 centimeters. How much work is done on the nail? Well, it sounds like the hammer had a change in kinetic energy while pushing the nail in. Now, I'm gonna level with you, Troy. There's 2 ways to approach this problem. One way is more accurate than the other. I'm gonna show you what I think is what I would expect you guys to do. And then you might ask a question. If you do, I'll say, well, yes, to be more accurate, we should do something else, okay? There's a change in kinetic energy of the hammer. This has to equal the net work done on the hammer. That change in kinetic energy was negative 20 joules because the hammer was brought to rest and it had 20 joules of energy and it was all kinetic. And now it's brought to rest, so it lost 20 joules of energy. And that happened because there was a force on the hammer from the nail as the hammer was pushed into the wood a certain distance. You following all that? And I'd say that the force was in the opposite direction of the displacement of the hammer. The hammer went downwards, but I think the force went upwards on the hammer to push it downwards. Now that displacement was 0.5 centimeter. So that's 0.005 meters. So if I solve this for the force on the hammer, I get 4,000 newtons of force on the hammer. Now, Newton's third law would tell, the chair's totally in the way. Newton's third law would tell me that if there's 4,000 newtons of 4,000 newtons of force done on the hammer, or force applied to the hammer, then there was 4,000 newtons of force on the nail. So I'd probably answer it there and say that's the answer. Now, there's something we're not taking into account. Do you know what it is? Okay. And I didn't know if it would come up or not. And you might, once you hear it, you might say, yeah, I was thinking like that, but maybe not. The truth is the nail went downwards a small amount, suggesting that the hammer had a little bit of potential energy that we didn't take into account because it was not actually at its lowest point. Does that make sense? That amount of potential energy is based on being at a height of 0.5 centimeter, which if we multiply 2 times 10 times 0.005 to find out how much energy we're talking about 0.1 joules of energy. So I'm not sure that this really affects the answer very much, but gravity did a little work on the nail too that we didn't include in this. But I don't think that it really makes that big of a difference because the nail moves such a small amount. Does that make sense? Now, if this were mechanics, yeah, I'd probably be having to make the kids deal with that. Probably would. But this isn't mechanics, so we're good. I think that's it, isn't it? Oh, there's more. What was the average force applied to the nail from the hammer? We got that. How much work was done on the hammer by the nail? 20 joules. 20 joules. Same force, same displacement, so 20 joules. So this is the next number 2, which comes after number 4. Figure that out. A 30-degree frictionless ramp is 6 meters long. The ramp is used to load boxes onto a truck. What is the height of the truck? All right. I guess I'll draw this first because I think that would be better for all of us. There's my 6 meter long ramp. I don't know why it's so large, but that's all right. And we'll make this the ground. And here's the back of the truck. I don't know, back of truck, wheel, I don't know, whatever, back of truck. And we're told that it's 6 meters long. This is 30 degrees. Is that all right with all of you? Good enough picture? The first thing it asks is, what is this height? So that's just a triangle problem. So if this is the opposite side and this is a hypotenuse, I would probably use sine of 30 equals opposite over hypotenuse or opposite over 6. So sine of 30 is a half, so the opposite side is 3 meters high. So this is 3 meters. All right? Not a problem. Let's move on. Question number B, how much work is done lifting a 15-kilogram box onto the back of the truck? So the work done in lifting a 15-kilogram box onto the back of the truck would be the same as the amount of gravitational potential energy that box would have once it made it to the back of the truck. So I'm just going to calculate the gravitational potential energy of the box when it's in the truck. And that'll be mgh. We're going to use 3 meters for the height and 15 for the mass. So 15 times 10 times 3. So looks like 450 joules, if I'm doing my arithmetic correct in my head. If you were to use the ramp, and if the ramp were magically frictionless, how much force would be required to push the box up the ramp at a constant velocity? And they have the audacity to say this is a force problem. And that audacity came from me. This is me telling you this is a force problem. So I'm not going to do the whole problem. We've done these before. So I'm of a mind that you know that the component of the weight down the ramp is mg sine theta. Right? You guys know what I'm talking about? Good. So I have to apply a force up the ramp so that the net force is 0. It says I'm going to be pushing the box at a constant velocity. So that means my applied force minus mg sine theta has got to be equal to 0. So that suggests that I have to apply a force equivalent to 15 times 10 times the sine of 30. So that's going to be 75 newtons of force. As the ramp is 6 meters long, how much work is required to push a box up the ramp? Okie doke. Now, we've done this problem. We did it differently before, but this is the same kind of problem. The work done will equal the applied force times the displacement times the cosine of the angle between the applied force and the displacement. So I am applying 75 newtons of force over a distance of 6 meters, and the force is in the same direction as I'm moving. So 6 times 750, which, boy, I bet that's going to be 450 joules. It's got to be the same amount of energy. Uh-oh, there's actually a coefficient of friction of 0.2 between the box and the ramp. Find the frictional force acting on the box. All right. Friction is equal to mu times the normal force. And in this problem, since the component of the weight into the ramp is mg cosine theta, the normal force and that force are balanced. So I can start by saying the normal force equals mg cosine theta. And if you think this is particularly complicated, it's not. We've done all these problems before. I am expecting that you can do this kind of stuff. So friction equals 0.2 times mg cosine 30. This is the size of the frictional force. So 150 times 30 cosine equals times 0.2. I get 26 newtons of force from friction. If the box is pushed at a constant velocity up the ramp, with friction acting on the box, what force would be required to push the box? Well, we already know that without friction, we have to push with 75 newtons. I'm thinking with friction, I'd have to push with 75 newtons plus 26 newtons. So 101 newtons of force. Is that all right, guys? I mean, I could redraw a force diagram and put friction over here, and we could rewrite it all out, but I think, can we spare me that? Good, good, good. I'm happy to hear that. I feel very spared. So, screw you, stupid T. That's the answer to F, so I guess we'll just keep going. How much work is done getting the box to the top of the ramp? All right, well, I'm applying 101 newton. This sounds like a repeat of a problem I've already done, but let's go with it. Work equals my force times the displacement times the cosine of theta, but because there's friction now, I apply 101 newtons of force over a displacement of 6 meters, and my force is in the direction of motion, so it's cosine of 0 degrees. Looks like 606 joules of energy. That's how much work I had to do. So, quite a bit more. You know, friction, you're going to pay a friction toll there. So, H, clearly the amount of work done in part G, which is realistic, is more than the amount of work done if you simply lifted the box up to the back of the truck as in part B. Why would I use a ramp if it takes more energy? Anybody have a good answer for that? There's a couple of answers, a couple of ways to approach it. Let's talk about the first thing. If we look at the picture, if I wanted to just put the box right in the back of the truck and just lift it straight up, I'd have to apply a force that's equivalent to the weight of the box. So I'd have to push upwards with 150 newtons of force. That's not terrible, but that's what I would have to do if I just push it up the ramp, I only have to push with 101 newtons of force. So maybe, if I'm doing this all day long, maybe the first or second box might not be a big deal, but maybe by the 10th or 20th box, I might start getting tired of having to apply that much force. So the ramp allows you to use less force. Even though there's friction, it's still less force. The other thing is, you know how tall 3 meters is? That's the ceiling. Right? I am just under 2 meters tall. You might not be able to reach. You might have to use the ramp. So I'd argue that there's 2 reasons. One is because the ramp allows you to get to higher places, and 2, you may not be able to lift with that much force. Now, a 15-kilogram box is only like 40 pounds. 40 pounds is nothing to sneeze at, but that's like, imagine lifting 40-pound plates to the gym and throwing them up on top of a truck 3 meters high. You might get tired after a while. The ramp would make it less. So our block of mass M has initial velocity of v on a frictionless track. The track includes a loop of radius r, after which there's a ramp. Find an expression for the minimum velocity of the block at the top of the loop in terms of r, m, and any fundamental constants that will allow the block to successfully make the trip without losing contact with the track. So although it starts off here, it's really asking about the block when it's here. And it's saying what is the minimum velocity the block has here, v min, so that it stays in contact with the track. Now, this is a force question. This is not an energy question. And we've done this question before. This is a kind of one of those ones we did in the last unit. So I'm going to approach this as a force problem, and I'm going to ask you guys, if the block is at the top of the track, what forces are acting on the block?
Normal.
Normal. What direction do I draw that?
Down.
Okay, so I have a normal force downwards. Anything else? What's that?
Gravity.
Gravity. So I have a gravitational force downwards. Those are the two forces acting on the block when they're at the top of the ramp. This is a net force equals MA problem, and not just A, but AC, because it's traveling in a circular path. The block is accelerating. So I'm going to make downwards the positive direction. I will be reminded that the track has a radius of r, and I'll proceed with the problem as normal by saying normal force plus weight will be equal to m v squared over r. Now, as we've discussed a number of times, velocity is related to how much force there is. If I go faster, I will need more force to make the turn. I have to push harder on it to get it to change direction. In looking at this problem, the weight can't change, but if v gets bigger and bigger and bigger, I just have to add more and more normal force. So follow that to its logical conclusion in the other direction. If I want to go slower and slower and slower, I provide less normal force. The slowest I can go is when the normal force is 0. That is my minimum speed to stay in contact with the track. Now that I know that, I can find an expression for the minimum velocity in terms of the given quantities. So I can get rid of the m's because there's one in every term. I can multiply both sides by r. And I can take the square root of both sides, and this gives me the minimum velocity. And we've done this problem a bunch, so I don't feel too bad about it. Let's see. Find an expression for the height the block attains after successfully traversing the loop in part A in terms of r, m, and any fundamental constants. All right. I'm constrained in that my answer has to be r, m, and fundamental constants. I'd say that right now, if I choose this as my reference level, does that make reasonable sense to make down there the reference level? Then the block, when it's at the top of the loop, has two kinds of energy. It has gravitational potential energy because it's above the reference level, and it has kinetic energy because it's moving. Everybody okay with all that? Now, an important detail here, something you need to keep in mind, is that this is the total energy of the system. Because if there's no losses, no matter where the block is, it should have this much energy. And we're being told the block is going to make it to some place along the ramp. And they'd like to know how high along the ramp it is. Now, to be honest, not that this is drawn to scale or anything, but when it makes it to its maximum height, it won't have any kinetic energy. Because if it had kinetic energy, that would mean it's moving, so it's either still going up or it's already coming down. So the maximum height will be when all of that energy becomes gravitational potential energy. Everybody good for that? Now I'm just going to use capital H here as my symbol for how high it goes. I'm looking for H. So the The kind of energy it has here is gravitational potential, or mg times h. And that has to equal the kind of energy it has here, which is gravitational potential, mg. And what do I put here for h minus h naught? 2r, that's right. It is 2r high because it's the top of the loop. Plus 1/2 m v min squared. Any questions about where I got any of that from? Alrighty. This is 2 mgr plus 1/2 m. I can't have v min in my answer. So I have to substitute, but I just came up with an expression for v min. That's in terms of g and r, and both of those can be in my answer. So square root of gr squared. And that has to equal mgh. So 2 mgr plus, I'm going to square the gr there and get 1/2 mgr equals mgh. What you looking at, Zach? You're somewhere else, aren't you?
No, I'm just trying to.
Yeah?
No, I'm just trying to focus.
No, you're not. That's silly, but okay. Just watching it, looking at the blank piece of paper,
No, I just,
and it's kind of funny. It was comical. I've been watching for like the last 10 minutes, so it's not like it's just been like just now. And I'm like, that paper is just not that interesting. But all right, you do you, my friend. You do you. The left side's 2 plus 1/2, so that's just 5/2 mgr, and that equals mgh. Do you notice that there's an mg in all the terms? So I just cancel the mg out. So I get 5/2 r equals the height. That's how high it's going to go. Since this is only a model of a real roller coaster, a spring launcher is going to be used to launch the block into the looped section. The block is pulled back against the spring launcher and released. The launcher has a spring constant of K and is a linear spring. What displacement of the spring will successfully launch the car through the loop in terms of M, R, K, and any fundamental constants. All right, so that spring launcher is somewhere that precedes the start of this ride. So it's over here someplace. So I'm going to say the box started out over here against some spring. And it has a spring constant of K. Now, you guys might not buy into this, but this is right here the total amount of energy in the system. Right? It is the sum of the potential energy and the kinetic energy the box had at the top. And it's already in terms of mg and r. So I'm going to use that as the total energy in the system. But over here, we have elastic potential energy, which is 1/2 K delta x squared. I'm just going to set that equal to 5/2 mgr. We're solving for delta x, so it's algebra again. Cancel out the 2's, get K delta x squared equals 5 mgr. Divide both sides by K. Delta x squared equals 5 mgr over K. And delta x equals the square root of all that. All right. So we've done all the math stuff. It is found that while using the displacement of the spring in part C, the block consistently loses contact between the block and the track as it makes its way around the loop. Two students argue about the reason why, and student 1 indicates that the spring is likely not perfectly linear and it holds less energy. than it should at the displacement they calculated, while student 2 believes that there is friction along the track. Although both students may be right, each student proposes a test to determine who is more correct. Student 1 suggests pulling the spring back further and trying again. Student 2 suggests starting the block on the ramp and running the block backwards towards the spring. Which student's test has a better chance of determining who is right? Please explain thoroughly. I'm going to pick on each table to tell me which student they think is got the right test. I'll give you a minute to confer, and then I'm just going to call you out.